Okay, good morning again. So let me recall where we left off yesterday. Namely, we had shown the following estimate. U is a zero Q form in the domain of d bar and the domain of d bar star. And this is less than or equal to d squared E over Q, d bar U norm squared plus d bar star U norm squared. Now this was still when omega has a C2 boundary. And of course, omega is bounded and pseudoconvex. All domains in my talks are bounded and pseudoconvex. But we do have still this assumption on C2 boundary. Let me, for some reason, this estimate is estimate 9 in my notes. So I'm just going to stick to that. And as one of the exercises, I asked you to show the following. 9 implies very good things about the images of d bar and d bar star, and about decomposing L2 0Q, namely, so it implies, first of all, it implies, firstly, that the image of d bar, now Q minus 1 star, that image which sits inside L2 0Q omega, this is closed. Actually, I got this wrong. No star there. But similarly, the image of d bar Q star which sits also inside here is closed. Note of course, d bar Q minus 1 has closed image. It then follows on general grounds that the image of its adjoint is also closed, but that's not this image. That's sitting in the Q minus 1 form. So this is not a redundant statement in that sense. So it implies that. Second, we have a nice orthogonal decomposition of L2 0Q into the kernel of d bar Q plus the image of d bar Q star. In general, there would have to be a closure here, but because these images are closed, we don't need that, right? But notice this is an orthogonal decomposition, because things that are in the image of d bar Q star are going to be orthogonal to things in the kernel of d bar Q, right? Thirdly, the image of d bar Q minus 1 is the kernel of d bar Q. Of course, this image is contained in the kernel just because we have a complex d bar followed by another d bar equals 0. But the point here is you get the whole kernel. And similarly, of course, for the image of the adjoint, image of d bar Q star is going to be the kernel of d bar Q minus 1 star. And here we have, well, in both cases, well, technically, here I have 1 less than or equal to Q less than or equal to N. Here I have 1 less than or equal to Q less than or equal to N minus 1. let's see, because, well, what happens here if Q is equal to N? Well, d bar Q is just a zero operator, and so there's not really. Okay, and maybe 4, sort of a corollary to all of this, if U is in L2 0Q, then I can write U as d bar V plus d bar star W, where, well, V, I might as well, if I can do this, I might as well take V to be in the kernel, in the orthogonal complement rather of the kernel, and W in the orthogonal complement of the, let's see, that will be the d bar Q star. So this wants to be really d bar Q minus 1, and this wants to be the adjoint of d bar Q, right? And maybe the most important part, I have this control of the norms. Norm of V plus norm of W is less than or equal to d squared E over Q to the 1/2 times the norm of U. Well, if you believe 1, 2, and 3, 4 follows, look at 2, you can write, so split U to something in the kernel of here, plus something in the kernel of that adjoint. And then, because of this, that the portion here in the kernel of d bar Q is going to be d bar of some V, right, because of this. And you can take this V orthogonal to the kernel of d bar Q, and then if you use this estimate, you get... So say again. Oh. So I should get what? Oh, here you mean? Yeah. Right. So, yeah, maybe something like that. So, let me put it like that. Some constant independent of everything but D, right. Okay, by the way, on this estimate, I didn't point this out yesterday, but it's quite remarkable, this constant here. Namely, it only depends on the domain via its diameter. That is the first thing that is remarkable. The second thing that is remarkable, it is independent of the dimension, n. It's not a priori clear why you should have something like that. Okay, now the importance of this property 4 here lies in the fact that it is preserved under taking increasing unions. Number one, and the second part, 4, is actually equivalent to the inequality 9. That's not hard to check. I mean, we've already seen that the inequality 9 implies this, and it's not hard to check that when you have this property 4, you get an estimate like this. And if you're careful here with the constants or write it with the squares, it actually comes out correctly to having the exact I suspect if I put squares everywhere, it's probably correct, and without the 1/2. Let's try this. Okay, well, so why is this significant? Well, this is now significant because this allows us to get rid of the C2 assumption. If omega is any pseudoconvex domain, by definition, it can be exhausted by C2 pseudoconvex domains, right? Those C2 pseudoconvex domains all have this property, and therefore, because it's invariant under increasing unions, omega will have this property, and because the property is actually equivalent to 9, this is now going to hold on any pseudoconvex domain without boundary smoothness. Let me formulate this as a theorem at long last. Theorem 2. So omega is in Cn. Bounded pseudoconvex with diameter d. Then for u in the domain of d bar intersect domain of d bar star, we have the estimate u squared less than or equal to d bar u squared well, d squared e over q times this. Okay. So it just takes some extra work to, if you don't assume any boundary smoothness, you have to do something. And one way is to rewrite this estimate here. And the way I've done it here with this property, and this property turns out to be relatively easy to check that it is invariant under taking increasing unions. It's also easy to check that it's actually not just a consequence of 9 here, but it's equivalent. And so we get the theorem then. All right. So now we have everything in place. I'm going to start now sort of part 2, which is the complex on the complex Laplacian. And the Neumann operator. Okay, so this form d bar u, d bar v, plus d bar star u, d bar star v, plays an important role, so let's give it a name. This is usually denoted as Q, U, and V. And of course, when I write something like this, I'm assuming that U and V are in the appropriate domains. That is, both are in the domain of d bar, intersect domain of d bar star. And we can take this as an inner product on the intersection of these domains. And with this inner product now, this intersection is going to be a Hilbert space. And well, why? Because, well, what you have to check is the completeness, but that's precisely our estimate there, if the d bars and d bar stars of a sequence converge, then the sequence converges as well, and then it's easy to check that everything works with the limit. So in view of, I guess, theorem 2. Okay. All right, so now let me define box Q. Okay, so now we've got two Hilbert spaces. We have got L2, 0Q, and then we've got the smaller space, but with a more strict norm, if you will, right? So box 0Q is the following. One way to define it abstractly is just, well, here we have this quadratic, this Hermitian form. Associated to it is a unique self-adjoint operator, and that is what box Q is. i.e., a form U in domain D bar intersect domain D bar star, it's the form domain, is in the domain of box Q if well, if we have d bar U, d bar V, plus d bar star U, d bar star V equals box Q U V. In other words, U is in the domain of box if there exists some form in L2 so that this holds. So this thing should be in L2 0Q omega. Let's see. Yes? So that's just, I mean, there's a whole abstract theory of how you associate self-adjoint operator to a Hermitian form. There are some conditions on the form, but this is all satisfied here. Well, so that's all fine, but it's a little bit unsatisfactory because it doesn't exactly tell you concretely what box Q is. In other words, it doesn't tell you what, if U is in the domain of box Q, how do you compute box QU, right? But this can be remedied. It's not hard to give an explicit description. But I wanted to also give this abstract because that's how you often see it in the literature. And then the explicit description is sort of assumed, but why it's the same thing is usually kind of swept under the rug. So let's formulate this as lemma 1. And namely, the domain of box Q is what you sort of think it should be if you look over here. If d bar U was in the domain of d bar star, you could take this over here. And d bar star U was in the domain of d bar, you could take this over here. And then what you would get here would be d bar U plus d bar star U. And so this actually turns out to be what it is, namely this domain is, well, first of all, U has to be in the domain of d bar intersect domain of d bar star, so that now U, no, d bar U is in the domain of d bar star, and d bar star U is in the domain of d bar, and then, that is, if U is in this domain, box QU is, like what I said, we think it should be d bar star U plus d bar star d bar U. Well, proof, or sort of sketch. So looking up here at this equation for these two sets, the inclusion this way, this is clear from what I said over there, right? If the d bar and d bar star are in the appropriate domains, we do the integration by parts and we get this. So we need to look at the other. Right, so I need to take a U that's in the domain of box Q as defined over there, and need to see that, and then d bar and d bar star U are in these domains, right? Okay, so domain of box Q, and let's check that d bar U is in the domain of d bar star. Well, so I have to pair d bar U with d bar of something, right? Well, from this definition, I know something if I have not just this d bar U with d bar of something, but I also have the term d bar star U and then d bar star of the same thing. So what to do? Well, the thing to do is to observe that instead of taking d bar V, it's the same thing of taking here this, where PQ is the Bergman projection on Q forms. So L20Q omega to the kernel of d bar sitting inside there. So the identity minus that is the orthogonal projection, well, onto the orthogonal complement. But the equality here is clear now, right? Because d bar of PQV is 0. So I can do that. Why does that help me? Well, because now I can add the term with the star. Because, like I said, this projects onto the orthogonal complement of the kernel of U, which is the image of d bar star, but that's also in the kernel of d bar star. So that thing is just plain 0. Pardon me? The second one is a V, you're right, I'm sorry. right? But now I have the form that I have over there, d bar u, d bar of something, plus d bar star u, d bar star of something, because u is in the domain of box Q, that is box QU paired with that something, which in our case is I minus PQV. But I minus PQV is self-adjoint. It's a projection. I'll take to the other side. It's I minus PQ, box QU comma V. All right, so now we have d bar U, d bar V is this, comma V. So that shows that d bar U is indeed in the domain of d bar star, and its d bar star is this, right? So let me write this down. I minus PQ, box QU, and similarly one can check that d bar star U, in other words, d bar star is in the domain of d bar, and this is going to end up being BQ of box QU. I mean, the way you check this is you view d bar as the adjoint of d bar star, and then you do a pairing with the stars and the same thing. And now you get box QU is d bar star U plus d bar star d bar U, right? Okay, so that's the sort of for computational purposes, that's the description of the box you want. But it is useful to also have the more abstract point of view. Okay. So now, denote by J sub Q the embedding of dem d bar intersect domain of d bar star into then theorem 2 just says that JQ is bounded, right? And the norm of JQ is less than or equal to, what is it, d squared E over Q, I guess, square root of that, right? Yes, I think so. So at this point, what that norm is not that important. The crucial thing in theorem 2 for our purposes is that JQ is bounded. All right. Okay, so now we have the complex Laplacian. Why is it called the complex Laplacian? Was an exercise that box QU, well, or let me write out the form now, summation prime J equals Q, Uj, dCj bar, and assume U is in the domain of box, that is just minus 1/4, and then it acts diagonally as the Laplacian. The usual Euclidean Laplacian. In fact, this has nothing to do really with U being in the domain of box Q if instead of box Q, you take d bar theta, formal adjoint plus theta d bar, you get this. That's just a computation. That is not true on general complex manifolds, by the way. It is true on Kähler manifolds. but not on general complex manifolds. But so it's a sort of Laplacian. It's also it's a Laplacian in the sense, and that's maybe the better analogy, if instead of d bar you use the total differential, the de Rham differential, right? Then this formula d star plus d star d just gives you the Laplacian on the Riemannian manifold. And so that's analogous, right? Okay. Well, and just as it is important there to invert this guy, it is important in several complex variables to invert box Q, and that is what's known as the de Neumann problem. Okay? So, well, here's the theorem. This guy turns out to be invertible indeed. By the way, before I do that, let me mention, I forgot to mention this, but note that we have this formula here. We have box QU is d bar u plus d bar star u, right? So this tells us something about the kernel of box Q. Namely, if using the kernel of box Q, we got these two guys are equal to 0, so by theorem 2, u is 0, right? So box Q has a trivial kernel, so at least right off the bat, there is some invertibility there. It's invertible on its image, of course, right? But what sort of operator that is not a priori clear. Well, it turns out box Q is actually onto. Once you know that, you could argue abstractly. If it's onto, from what I've just said now, we invert it. The operator has a closed graph because box Q has a closed graph. And so then, since it was onto, this is now an operator with a closed graph on a Hilbert space, so it's going to be bounded. But we can give an explicit formula for this inverse. That inverse is called the de Neumann operator and Q. It gives an explicit formula in terms of this embedding JQ. Okay, so theorem 3, so again, omega bounded pseudoconvex. Here n should be at least 2, d diameter of omega. Let's see what else. 1 less than or equal to q less than or equal to n. Then there are many parts to this theorem. 1, box q equals d bar star plus d bar star. D bar is a self-adjoint, well, unbounded. Self-adjoint surjective operator on L2, 0q omega. Note that it's obviously symmetric from this form, but symmetric is not necessarily the same as self-adjoint, but here it is. Well, and having now a bounded inverse, NQ, and it's given in terms of this, where is it, in terms of this embedding Q here, namely it's JQ star and then composed with JQ. No, JQ star maps from L2 into here, and then we embed back into L2. Well, so if this is true, if this operator does invert box, then certainly it's a bounded operator, and and we get a norm estimate from the norm estimate in JQ. Also, then it's clearly self-adjoint. So 2 is now a bunch of norm estimates, which like I say, are going to be easy to get from those for JQ, and of course JQ star is the same norm, namely NQU norm squared, nope, just norm less than or equal to E squared E over Q of U, D bar star, NQU norm squared, here I'm on squares, plus D bar star NQU norm squared less than or equal to let me see here. Yeah, I think that's correct because I get the norm of JQ star, that's the same as norm of JQ, and here once more, so it's a square of that norm, so yeah. Thirdly, so these things are easy. The main thing is going to be to show that this is really an inverse box, but also there's some useful commutation properties. D bar and QU is the same as NQ plus 1 D bar U. This is for U in the domain of D bar. Similarly for the adjoint D bar star, NQU is the same as NQ minus 1 D bar star U. U in the domain of D bar star. And here, strictly speaking, let's take Q at least 2, because we haven't really talked about N0. And finally, it's a formula for the Bergman projection. PQU is U minus, well, it's really D bar star D bar N Q plus 1, no, and Q minus 1 U, but I can also write it as U minus D bar star and Q plus 1 D bar U. This is not, okay, this wants to be a Q. And in this form, it's usually called Kohn's formula. And I think the reason why he wrote it down like this is because he's mainly at the time interested in P0, the Bergman projection on functions, and then you don't want to deal with N0. You could, but it gets sort of artificial. So you can write it like this. Notice, this really is the Bergman projection because the result is D bar closed. If you take D bar U here, get D bar U here, you just get D bar U. The end's going to go away. So it's D bar closed, and you subtract something from U that's orthogonal to the space onto which you project, so to the Bergman space. So that is the Bergman projection. Before we look at the proof, here's a quick corollary for solving D bar. Pardon me? Which one? NQ? Not in general. No. In general, it's just L2. That's actually going to be later in the week. That will be the topic of a discussion when it is compact and when it's not. In general, it's not compact. So corollary here, well, we can solve D bar and D bar star. If U is in the kernel of D bar Q, say, then D bar star and Q U solves D bar of that equals U. And similarly, if U is in the kernel of D bar Q minus 1 star, then d bar star of d bar q and qu equals u. So let's see, this is nq and q plus 1, so this wants to be at adjoint. Well, to see that, for instance, to see 1, well, we know u is d bar star, and qu plus d bar star, d bar, and qu, right? By the way, notice this is what's sometimes or often called a Hodge decomposition, and in fact, introducing the whole Neumann setup originally was going back to Spencer, was actually in an attempt to do Hodge theory on manifolds with boundary. Okay, but now, if U is d bar closed, well, this is d bar closed, so it then follows this also has to be d bar closed, but it's d bar of something, so it's also orthogonal to the kernel of d bar. So this has to be 0 if d bar u equals 0, and so now you got it. And so it gives you d bar star n, gives you a solution to the d bar equation. Moreover, it's orthogonal to the kernel of d bar, so it gives you the solution that has minimal L2 norm, right? The one that's orthogonal to the kernel gives you the one with minimal L2 norm. Okay, so let's look at theorem 3. So, well, I'm not going to prove every single point. Did I? No, okay, it didn't erase the theorem. Good. Yeah, these estimates follow easily from this. Here one has to do, well, let me not say anything there. Let's look at this first, that if I define my NQ as JQ star composed with JQ, that really does invert box, right? So I start with U in L2, and well, this is in the domain of d bar intersect domain of d bar star, so that's good, because JQ star maps into that domain, and then this just embeds it, doesn't change anything. So that's the first requirement for being in the domain of box, right? Has to be in the domain of d bar and d bar star. And then we have to check that wrong sheet. To check now that this wants to be a U, that this is really in the domain of box. Well, so what do we have to check? We have to take d bar of the thing. Pair it with some d bar v, and then d bar star. And then there should be something here, v, right? But let's see here. So we have JQ star of U and then JQ d bar. Well, taking d bar of this, when I view this as sitting inside L2 is the same as taking d bar when I view it as sitting inside the domain at d bar, intersect domain d bar star. It's the same d bar. And similarly here. But now, look what we have now. This is just an inner product in the graph norm between JQ star U and V. That's the inner product in the graph norm on domain D bar intersect domain D bar star, right? Okay, but just by the definition of the adjoint, that is U, JQV, now just the L2 inner product. It is. I mean, I know this is something I figured out many years ago, and it was a first surprise, but it's okay. It works. It's all good. But now I can do the same thing again. I mean, this inner product, that's just UV. So now we have what we want here. So now this tells us that JQ star U is in the domain of box, and box is equal to this. Okay. So this is a handy little device with this embedding of sort of giving an explicit description for the Neumann operator. And of course, the motivation for defining it in this way is, if you look what you want, you're basically looking at this, but here you would have an NQ, and here you would have an NQ. And so then you find that as an operator into domain D bar intersect domain D bar star, it has to coincide with JQ star. And then to view it as an operator into L2, you put JQ, you compose it with JQ. And you get that. Okay, now to check the other, that JQ star box Q U equals U is now easy using the fact, for instance, that box has a trivial kernel. So let's just stop the proof here. Like I said, the estimates are easy from the estimates for JQ star. All right. Yeah, well, you can't, I mean, the way people used to set it up for NQ, you can set it up so that you can use the Ries theorem in Hilbert space. And that's sort of underlying that, I believe. It's right. But it will be, for a number of reasons, actually, for us, when we discuss compactness in particular, this form is going to be useful because an operator like this is compact if and only if JQ is compact, and that will be useful to know. All right. So now, this is preparation for tomorrow. We have managed now to get rid of the C2 assumption on the domain in our sort of basic estimate. But remember where that came from. That came from an estimate that sort of looked like this: some prime k equals q minus 1 some jk, and then we had e to the b, d square b, dcj, dck bar, ujk, ukk bar, and, well, the integral. That was less than or equal to d bar u squared plus d bar star u squared. Right, where we had b twice differentiable on the closure and b less than or equal to 0. Now that, for that, we still have the restriction that omega is C2. Well, we're going to need this formula again for arbitrary, or this estimate, if you will, for arbitrary omegas. And that's not going to be a matter of, well, we'll still use the exhaustion by C2 pseudoconvex domains, but some more work is needed. Namely, if we have here an omega, and here is one of the exhausting domains, say omega nu, and let's just take one forms. Let's take a one form summation uj dcj bar. Remember, the boundary condition is for being in the domain of d bar star is summation uj d rho dcj equals 0 on the boundary. Say u has C1 on the closure coefficients. Well, there's no reason when you restrict u to omega nu that this condition should hold here. However, if we want to use this estimate in omega nu, we need forms in the domain of d bar and d bar star. Okay? Well, now that we do have the d bar Neumann operator, we can use it on the omega nus to deal with this problem. And we're going to have to use here that all these estimates are, only depend on the domain by the diameter, so they're all going to be uniform in nu. And the result, which I'm going to write down, and then we'll see how to prove it. So omega is bounded pseudoconvex. U in the domain of d bar intersect domain of d bar star. Then, well, there was another part that concerned bar derivatives of the coefficients, so we can also get this summation over j, summation prime, summation j goes from 1 to n, duj dcj bar, norm squared, less than or equal to d bar u norm squared plus d bar star u norm squared. And the second one, where we here take b and c2, let's take in c2 at a closure. In practice, it's not going to matter. We will have summation prime, k equals q minus 1, summation j, jk, goes from 1 to n, e to the b, d square b, dcj, dck bar, ujk, ukk bar. That wants to be integrated over omega. Okay, so let me just show you how one modifies the restrictions of the form u to these omega nus. Okay, so omega is the union of these omega nu's, and this is sort of an increasing union, and omega nu's over C2. Okay. So here's what I do. I define the following form on omega nu. We define the form u nu. It should be the following. Let me just write it down and I'll explain it a little. D bar, and I use subscript nu for the operators on the omega nu's. So d bar nu n q plus 1 nu of what? Of d bar u restricted to omega nu plus d bar nu and q minus 1 applied to, well, instead of d bar, well, it's d bar star u, but let me just write the formal adjoint. It's the same thing on omega nu. Just, I mean, you can write d bar star here. It's the d bar star on omega, which is the same thing since using the domain of d bar star as just the formal adjoint. Okay, well, first of all, let's see that we produced something that is in the domain of d bar and in the domain of d bar star on omega nu. Well, the first term, because n here, this is going to be in the domain of d bar. This is in the kernel of d bar, so we're in the domain of d bar. Similarly, this is in the kernel of d bar star. Here, nq maps into the domain of box. So d bar nu of nq here is in the domain of d bar nu star, right? So the domain of d bar on omega nu. Okay. Moreover, if I take d bar of u nu, this term goes away, and then here I just have d bar star, and so this is a projection. So the norm of d bar u nu is less than or equal to the norm on omega nu, less than or equal to d bar u restricted to omega nu. The norm on omega nu, that's dominated by the norm of d bar u. And similarly, d bar star this part goes away, its projection here is going to be dominated by d bar star u, the normal L2. Okay, now, and this I'm just going to indicate, don't really have time to do the details. So now one applies, let's say 2 here, one applies 2 on omega nu to these forms. One then would like to let nu go to infinity to obtain this. Well, one has to be careful. What one has to do is fix a fixed relatively compact subset omega hat. Look at this integral over omega hat, but with the u nu's. Then one lets nu go to infinity. One then has to show that these u nu's have limits on any such omega hat that equals u. one can show that. And then using these uniform bounds that I've started to indicate there, one gets that this quantity, but integrated over omega hat, is dominated by the right-hand side, and omega hat was arbitrary. And so one gets that. Now, this is a bit more involved than I'm letting on here. One needs to use, for example, that the interior ellipticity of d bar and d bar star. In other words, one needs to use that on a relatively compact subset, one can control the sub F1 norm in terms of d bar and d bar star. Because sub F1 embeds compactly into L2, that gives a certain compactness which allows to have convergent subsequences, and then the whole machine works. The details are, I mean, I've written a monograph on d bar Neumann, so the details are in there. Unfortunately, the EMS has the copyright, so I couldn't just hand out, you know, my LaTeX files for that. But that's where you find details. Also, I'm happy to sit down and, you know, go through the whole proof if you really want to know it. All right, so now what we're going to do tomorrow is we're going to use this in the following way. If you look here, remember, we're interested in compactness of d bar Neumann. By what we've said before, that's going to be equivalent to compactness of the embedding JQ. Well, look at this. If we have functions B that qualify here, that have a huge Hessian, somehow that should then tell you, that should be good for compactness, that should tell you, right, if this is huge, there will be some huge constant times the norm of u, and some error terms, so this would tell you then that the norm of u is dominated by 1 over huge constant times this, plus some weak error terms. And that, according to a functional analysis lemma, is in fact is equivalent to compactness. I'll state the lemma tomorrow, so thank you.